So in last lecture, we have seen simple harmonic motion, and we have seen example of spring mass system. So here this is spring mass system. I have taken vertical spring mass system. K is force constant of the spring and M is mass attached to the spring. So here this position we can call this as equilibrium position. So let us take this as x is equal to 0. And if we extend this to this up to this one and release, it will oscillate between these 2 points. So it will oscillate between plus A and minus A. So what happens? Here force, it is equal to minus kx. We get differential equation m d2x by dt square plus kx is equal to 0, or we can write this as d2x by dt square plus omega square x is equal to 0, where omega square is k by m. And we get solution of this, that is called equation of HSM. It is x is equal to a sine omega t plus phi, and this omega t plus phi, it is called phase, this one, and a is called amplitude of oscillations. Now here we get velocity, that is dx by dt, it is equal to a omega cos omega t plus phi. So velocity is omega under root a square minus x square. Similarly, kinetic energy, it is 1/2 mass into velocity square. So it comes out to be 1/2 m omega square in bracket a square minus x square. And potential energy, that is 1/2 m omega square x square. And total energy is 1/2 m omega square a square. So total energy is constant. Total energy is constant. And here period of oscillation t is equal to 2 pi upon omega, that comes out to be 2 pi under root m by k. And frequency of oscillations mu is equal to 1 upon t, it comes out to be 1 upon 2 pi under root k by m. And we have seen lot of examples on this, lot of multiple choice questions on this. Now we'll go to next topic, that is also important topic, that is composition of two simple harmonic motions. Composition of two simple harmonic motions means two simple harmonic motions acting on the oscillator simultaneously. Here again we have taken example of spring mass system. So consider two SHMs being executed along the same line, say x-axis. The two SHMs have same period t, but have different amplitudes and has a phase difference between them. So here we have first spring. This is first spring having force constant k. Second spring, suppose having force constant k. And here this is equilibrium position. This is equilibrium position. So let us call this as x is equal to 0. Now here this one means here this one is equilibrium position of first spring. This one is equilibrium position of second spring. And suppose we extend this mass. So what happens? Equilibrium position of first spring changes. Equilibrium position of second spring changes. So here, and this is resultant one. And if we release it, now this system oscillates between this one and this one. So what happens here? We have two simple harmonic motions acting on mass simultaneously. First one due to first spring and second one due to second spring. They are acting simultaneously and along the same line. means I have taken this axis as x-axis. So here I can write x1 is equal to a1 sine omega t plus phi 1. This is equation of first SHM. x2, it is a2 sine omega t plus phi 2. Now omega is same because we have taken here same period. Same period. So what is resultant displacement? x1 it is due to first spring, x2 it is due to second spring. Resultant is x1 plus x2. And we know resultant force F is equal to minus kx, where x is x1 plus x2. So if we use this x1 and x2 here, we get x is equal to a1 sine omega t plus phi 1 plus a2 sine omega t plus phi 2. Omega t plus phi 2. And if we solve this, we get this one as. Now we'll not go in mathematical detail. So x is equal to, we'll get some r sine omega t plus phi. So here this is resultant motion. Now if we see resultant motion, that is also along x-axis. And it is also simple harmonic motion, where r is resultant amplitude. And what is this resultant amplitude? R, it comes out to be, if we solve this, we will get R is equal to square root of A1 square plus A2 square plus 2 times A1 A2 cos of phi 1 minus phi 2. So phi 1 minus phi 2, that is called phase difference, because here phi 1 and this is phi 2. These are starting phases of first and second simple harmonic motion. So this phi 1 minus phi 2, that is phase difference. So what is that? So R is equal to, we get here A1 square plus A2 square plus 2 times. So here we'll get we will get 2 times A1 A2 cos phi, where phi is phi 1 minus phi 2. This is about resultant amplitude. And now what is phi? So we can obtain phi using this one. Tan phi is equal to A1 sin phi 1 plus A2 sin phi 2 upon A2 A1 cos phi 1 plus A2 cos phi 2. So resultant amplitude depends on phase difference, and resultant starting phase depends on phi 1 and phi 2, A1 and A2. So this is general formulation for composition of two simple harmonic motions along the same line. Now we will take one case. Suppose first SHM is x1, that is A1 sin omega t, and second one is x2 is equal to A2 sin omega t plus phi. So phase difference, starting phase difference we have included here. So here again x is equal to x1 plus x2. So we get here x is equal to A1 sin omega t plus A2 sin omega t plus phi. And if we solve this, we will get x is equal to again here r sin omega t plus some, I can write here phi dash. So this is resultant. So resultant of two simple harmonic motions along the same line is also simple harmonic motion. Here R is again square root of a1 square plus a2 square plus 2 times a1 a2 cos phi and tan phi dash is equal to, now we will use this equation, a1 sin phi 1 plus a2 sin phi 2 upon a1 cos phi 1 plus a2 cos phi 2 here. So phi 1 is 0, phi 2 is phi. So we get here a2 sin phi upon a1 plus a2 cos phi. So we get this tan phi dash. Now suppose we take हे प्रेझेंटेशन दिसायचं बंद झालंय का? हॅलो रोहित.
यस सर. हो सर.
एक मिनिट मी नेट कनेक्शन चेक करतो. So here tan phi is equal to this and R is resultant one for these two simple harmonic motions along x-axis. So here this is example for that. Only we have taken x1 is a sin omega t, x2 is a2 sin omega t plus phi. So we get here this. Now we can have different cases also. So suppose we take simple cases we will take. So here I can take, suppose we have here phi is equal to 0. This is first case. So if we use phi is equal to 0, we will get r root of a1 square plus a2 square plus 2a1 a2 into cos 0 degree. Now cos 0 is 1. So we will get r is equal to root of a1 square plus a2 square plus 2 times a1 a2. And what is this? I can write this as square root of a1 plus a2 bracket square. So we will get resultant amplitude is a1 plus a2. And tan phi dash, now phi is 0, so sin phi is 0, so this is 0, so we will get phi dash is equal to 0. We get phi dash is equal to 0. Now we can take second case. Suppose we take phi is equal to pi degree, then we will get r is equal to square root of a1 square plus a2 square plus 2 times a1 a2 cos pi. Now cos pi is minus 1. So we will get r is equal to square root of a1 square plus a2 square minus 2 times a1 a2. So this is equal to square root of a1 minus a2 bracket square. So this is a1 minus a2. So this is r. Now we are going to see number of multiple choice questions on this. So we will see in that number of cases regarding this. Now what is tan phi dash? Tan phi dash, it is a2 sin phi upon a1 plus a2 cos phi. Now again phi is pi. So and sin pi is 0. So we'll get tan phi dash is equal to 0. So phi dash is equal to 0. So resultant starting phase is also 0. Now you can take case phi is equal to pi by 2, phi is equal to pi by 4, phi is equal to 3 pi by 2, like this. And corresponding to this, you will get different amplitudes and different phases phi dash. So that we will see in multiple choice questions. Now this is composition of two simple harmonic motions acting on the oscillator simultaneously along the same line. Now we will see another composition. Composition of two mutually perpendicular SHMs. Means one simple harmonic motion, it is acting along x-axis suppose, and another is acting along y-axis. I have taken here simple example. Suppose this is first spring and this is second spring, and they are attached to mass like this. These are fixed supports. And this is now third spring and this is fourth spring. And here these are fixed supports. So what happens, due to first and second, simple harmonic motion will act along y-axis, and due to third and fourth, simple harmonic motion will act along x-axis. So we have two simple harmonic motions. One is acting along y-axis and another acting along x-axis. So this is x-axis, this is y-axis. So if we displace this mass and release, that mass will oscillate. It will oscillate due to two simple harmonic motions. One is along x-axis, another is along y-axis. And what happens? This mass will move. This mass will move. And this mass will trace a path. Now that path may be circle, ellipse, straight line, figure of 8. That depends on characteristics of two simple harmonic motions. First we will see simple examples. Suppose all springs are identical. K, 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 K. These are force constants of the springs. So springs are identical. So I can take one simple harmonic motion that is acting along x-axis. Suppose x is equal to a sine omega t, that is acting along x-axis, and y is equal to, you can take b sine omega t plus phi. This is second simple harmonic motion that is acting along y-axis. And phi is starting phase difference between x and y. Now here frequencies are equal. Omega, they are equal because springs are identical springs. Then what is resultant path of the particle? Means resultant path along which that particle will move, that mass will move. So that we can obtain by eliminating omega t. This omega t from two equations. So you can eliminate. You can write here y by b is equal to sine omega t plus phi, and x by a is equal to sine omega t. Now y by b you can write sine omega t cos phi plus cos omega t sine phi, like this. And so you can write y by b is equal to sine omega t cos phi plus root of 1 minus sine square omega t multiplied by sine phi. And now use this here and here and solve it, rationalize and solve it. So if we solve this, you will get x square upon a square plus y square upon b square minus 2 times xy upon AB into cos phi is equal to sine square phi. So this is resultant path for two mutually perpendicular simple harmonic motions having the same frequencies. Means frequency of first and frequency of second, they are the same. So resultant path depends on amplitude A, amplitude B, and phase difference between two simple harmonic motions. Now, phase difference can be 0, can be pi, can be 2 pi, can be pi by 2, can be pi by 4, like this. So, suppose we have phi is equal to 0 degree, suppose. So, we'll get here what? X square upon a square plus y square upon b square minus 2xy upon ab. Now, cos 0 is 1. Sine 0 is 0, so you will get 0. So you can write this as x by a minus y by b and square of this is equal to 0. Now this one, so this one we can write x by a minus y by b is equal to 0. So x by a is equal to y by b. So we'll get x is equal, y is equal to b by a into x. So what is this? This is equation of straight line. Means on xy plane, this mass m will move along straight line. So it will move between these two. Here plus a, minus a, plus b, minus b. And you can find here slope of this, you will get b by a. But if we take phi is equal to suppose 0 degree, then what is phi is equal to pi. So if we take phi is equal to pi, is equal to pi, then what is difference? Cos pi is minus 1, sin pi is 0. So we'll get minus minus, here we'll get plus. And so we'll get what? X by a plus y by b bracket square. So x by a plus y by b is equal to 0. So x by a is equal to minus y by b, or you can get y is equal to minus b by a into x. So in this case, you will get path like this along this one. So it is straight path. So what happens? Particle will move back and forth along this line like this. It will move like this. It will. So path is straight line. Path is straight line. And slope is either b by a or minus b by a, depending upon whether it is 0 degree phase difference or pi degree phase difference, pi radians phase difference. So here, this is composition for 1:1. Now suppose phase is pi by 2, then what happens? So pi by 2, cos pi by 2 is 0, sin pi by 2 is 1, and you can find path. So in this way we get paths. So here you will get circle when phi is pi by 2 and a is equal to b. But if a is not equal to b, and suppose a is greater than b and phi is pi by 2, you will get elliptical path. If phi is pi by 4, you will get 3 pi by 4, you will get path like this. If phi is pi by 4, you will get path like this. Means this is ellipse, this is elliptical path. So you will get elliptical paths. Only they are oriented. One is like this, another is like this. So this, it is pi by 4, and this one it is 3 pi by 4. So this is about composition of two mutually perpendicular simple harmonic motions having the same frequency. So you will get path of particle, means that particle will move either along circle or along elliptical path or along straight line. That depends on phase difference and amplitudes. Now we will go to general one. Composition of two mutually perpendicular simple harmonic motions. The equations of motions for two mutually perpendicular simple harmonic motions acting simultaneously on a particles are given as x is equal to, suppose, a sin omega 1 t plus phi 1. So omega 1 is angular frequency for simple harmonic motion along x axis, and y is equal to b sin omega 2 t plus phi 2. So whatever resultant path of the particle, so the path traced by the particle depends on ratio, that is omega 1 upon omega 2. The amplitudes A and B and the starting phase difference, that is phi 1 minus phi 2. If omega 1 upon omega 2 a rational number, so that angular frequencies are commensurable, then the curve is closed curve. Closed curve is, see here, this type of curve is closed curve, and that figures are called Lissajous figures. So when particle is subjected to two mutually perpendicular simple harmonic motions, it traces a path on a plane that depends upon the frequencies, amplitudes and phases of the component SHMs. If the frequencies of two component SHMs are not equal, the path of particle is no longer an ellipse but a curve called Lissajous curve. So these curves were first demonstrated by Jules Antoine Lissajous in 1857. So suppose we have two simple harmonic motions. Here I have taken x is equal to a sin omega 1 t plus phi 1 and y is equal to b sin omega 2 t plus phi 2, and suppose frequency ratio is omega 1 to omega 2 is 1 to 1. We have already seen that. So we will get circle if a and b are equal and phi 1 minus phi 2, that is phase difference, is pi by 2. But if a and b are not equal but a is greater than b, then you will get elliptical path. If phase difference is 3 pi by 4, you will get elliptical path, but that ellipse is oriented ellipse like this shown in figure. If phi is pi by 4, you will get again ellipse but along this direction. Now suppose frequency ratio is 1 to 2, means omega 1 upon omega 2, that ratio is 1/2, or you can take 2 to 1. So suppose we take 1 to 2, you will get figure like this for a greater than b and phi is equal to pi by 2. If it is 2 to 1, then you will get figure like this, figure of 8 for a greater than b and phi equal to pi by 2. So see here, ratio is 1 to 2 and here 2 to 1. So here figure is like this and here figure is like this. Figure is like this. So what happens here? Means here what? We can write x is equal to a sin omega t and y is equal to a sin 2 omega t plus phi. Meaning of this is this. Frequency ratio is 1:2. What happens when there is one oscillation along x-axis? There are two oscillations along y-axis. So we get loops along x-axis. But in this case, 2:1 means we'll get here what? In this case, x is equal to a sine 2 omega t and y is equal to b sine omega t plus phi. Means when there are two oscillations along x-axis, within that time there is one oscillation along y-axis. And we get figure like this, 8. Figure of 8. So these are some paths depending upon phase difference. So if you can take frequency ratio 1:3, 3:1, you will get 3 loops, 4 loops if frequency ratio is 1:4 or 4:1 and so on. So in general, we know omega is under root k by 1, k by m. So omega 1 upon omega 2 is root of k1 upon k2. So k1 upon k2 is omega 1 square upon omega 2 square. Suppose frequency ratio is 1/2. Omega 1 upon omega 2 is 1 upon 2. It gives you k1 upon k2 is equal to 1/4. Now we'll go to another one, that is angular SHM. What is angular SHM? If path of particle or a body performing an oscillatory motion is curved, the motion is known as angular simple harmonic motion. So if we see here, this body it is moving along this curved path. That's why it is angular oscillatory motion or simple harmonic motion. So we define angular simple harmonic motion is defined as the oscillatory motion of a body in which the body is acted upon by a restoring torque or called couple, which is directly proportional to its angular displacement from the equilibrium position and directed opposite to the angular displacement. That is called angular simple harmonic motion. So here, suppose here we have torsional pendulum and suppose P is its equilibrium position, and if we displace here, the wire is twisted and the restoring couple will be tau is proportional to theta. That is tau is equal to minus eta theta. So according to second law, theta is called torsional constant of the support wire, means of this wire. Newton's second law gives tau is equal to I into d2 theta by dt square. What is I? I is moment of inertia. This I is moment of inertia of this disc about this axis, about this perpendicular axis. And if we take this here, tau here, we get I d2 theta by dt square is equal to minus eta theta. So here we get d2 theta by dt square plus k upon theta upon I, theta is equal to 0. So you can write d2 theta by dt square plus omega square theta is equal to 0. Here omega square, that is theta upon I. And solution of this is theta is equal to theta 0 sine omega t plus beta. So this is angular simple harmonic motion. And here we get omega, it is root of theta by I. So period of oscillation t is equal to what? 2 pi under root I by k. And in multiple choice questions we will see some different examples on this. Now let us see simple example of angular simple harmonic motion. Here we have simple pendulum. If bob is at position A, that is called equilibrium position. Now bob is displaced through angle theta. So it is at position B. L is length of the string and T is tension in the string. And at point B, downward force acting, that is mg. This mg, where m is mass of the bob. So mg is resolved into two components, mg cos theta and mg sin theta. Now mg cos theta and t, they are opposite to each other. So force responsible for angular SHM is mg sin theta. So couple, here it is mg sin theta into L, or it is equal to mgl sin theta. So torque is equal to minus mgl sin theta, and I can write here I into d2 theta by dt square plus mgl sin theta is equal to 0. Now for simple pendulum, moment of inertia is ml square, where m is mass of the bob. So we get here ml square into d2 theta by dt square plus mgl sin theta is equal to 0. So if we divide throughout by ml square, we will get this equation, d2 theta by dt square plus g by l sin theta is equal to 0. So this is differential equation for simple pendulum. Now if we take small angle, when the angle is very small, we have sin theta is approximately equal to theta, and equation becomes d2 theta by dt square plus z by l theta is equal to 0. So let us take this z by l as omega square. So omega square is equal to g by l. So period is t is equal to 2 pi upon omega. So we get t is equal to 2 pi under root L by G. So here we will see period depends on L only, and it does not depend on mass of the bob. So in next lecture we will see MCQs, multiple choice questions. On composition of simple harmonic motions as well as on angular simple harmonic motions. So thank you for this lecture. If you like my lecture, I request you to subscribe the channel by pressing subscribe button and also press like button. Thanks very much.